Today we're going to talk about angles in the Cartesian plane, so the x and y axis, because we want to get our angles out of the right triangles. Right triangles are really great for introducing the trig functions of sine, cosine, and tangent. And we use right triangles because it's really convenient to have opposite, adjacent, and hypotenuse. And solving right triangles is a useful skill to have. So that's all good. But we need to generalize everything that we do in math classes. And so what we're going to do is see what we can get out of these trig functions if the angles are not just angles in a triangle. So let's begin by talking about standard position. Like it says on the tin, we're going to be looking at the Cartesian plane. So there's going to be an x-axis and a y-axis. And we're going to use the usual. X-axis is the horizontal, and to the right is positive. Y-axis is going to be vertical, and up will be positive. That's the normal way we set up a plane. So the y-axis is going to be vertical, where up is positive. The x-axis is going to be horizontal, and to the right is positive. An angle in standard position will have its initial side on the positive x-axis. So the initial side goes on the positive x-axis. Standard position starts the initial side on the positive x-axis with a vertex at the origin. Counterclockwise is going to be the positive direction. So we'll rotate counterclockwise to be the positive direction, and then we'll keep going to the terminal side. So the terminal side we should note that the initial side and the terminal side are actually rays because they have a starting point that's at the origin, and then they're half a line. They go on forever. I am always going to call them sides. I've never been able to call them rays. So I'm going to infect you with that bug as well. Oh, that's a bad choice of phrasing, considering the current health situation. No one does. That's probably why I don't, because my math teacher didn't, and their math teacher didn't. So it goes back forever. There's probably like 4 or 5 math teachers that insist that they be called rays. And because so many people don't, they insist that much harder. You know what I mean? Like if it's like 1 or 2 people, they just like, oh yeah, whatever. But if it's like everybody and you feel singled out, go, no. This is why I don't say begging the question when I mean raising the question. I say raising the question, even though in modern English language, begging the question just means raising the question now. Because that's how language works. Words don't actually mean stuff outside of math. More like math. Math is the last place where words actually mean things. Anybody know the person that won't say literally just for emphasis? I'm really sorry, but literally can be used for emphasis now. You know how I could tell? Everybody does it. Because that's how language works. It is literally how language works. Math, not so much. You can count on it. So there's an initial side that we'll always put on the positive x-axis, and then we'll spin towards the terminal side. Where those two sides meet is the vertex, and that will be at the origin for standard position. The other aspect that we have to remember is that counterclockwise is the positive direction. So here is where we would call the label the angle theta. And we're going to remember that counterclockwise is positive. We always have to make sure we state what is the positive direction. Mostly because these things are arbitrary. We had to pick one. So we said, all right, to the right is positive. We read left to right. But we also read up to down. So I don't know why up has to be positive, but, or I guess it doesn't. But that's just the convention. Someone decided a long time ago, we're stuck with it now. It's one of those things that would be kind of a disaster to change. All of a sudden try to standardize down is positive. That'd be like saying, all right, starting tomorrow, we're all going to drive on the other side of the street. That would have a huge body count. It's actually been attempted in some other countries. Like, well, hey, let's just switch the side of the street we should drive on. And then it was like nothing but crashes because some people didn't get the memo. And they say, all right. Let's just go back to the way we were doing it before. Plus, that means that gives us the opportunity to design interesting intersections where you have one country that drives on the right side, another country that drives on the left, and then like a cool intersection where you just drive along and eventually you can switch sides. You like go through the interchange and say, hey, I'm on the other side of the road now. And the civil engineers are just sitting there and high-fiving each other. So this is standard position. Initial side on the positive x-axis, vertex at the origin, counterclockwise is the positive direction. This the Cartesian plane is broken up into 4 quadrants. We have 4 quadrants. In the upper right corner, we have quadrant 1. Which we abbreviate Q1. And for some reason, we use friggin' Roman numerals, even though they're terrible. Don't know how the Roman Empire got so big using these terrible numbers. So in the upper right corner, that's going to be quadrant 1. And then we count around counterclockwise. So over here, we have quadrant 2. Down here, we'll have quadrant 3. And below quadrant 1, we'll have quadrant 4. I'm pretty sure the book uses Roman numerals. That's kind of the standard thing. Next time we meet, I'm probably just going to use regular old 1, 2, 3, and 4. I'm trying to change that. It's kind of like radical symbols. I'm trying to get rid of radical symbols. We don't need this anymore. We should just use fraction exponents. But too many math traditionalists are like, oh, well, we should use radical symbol. They're not, in fact, radical. Just write 1/2 as an exponent. All right. So we know that going all the way around is 360 degrees. So each quadrant has a range of angles. over here on the positive x-axis, that's where theta will equal 0 degrees. An angle that terminates in the first quadrant will have a measure between 0 and 90 degrees. So we hit 90 degrees up at the positive y-axis. When we get to the negative x-axis, at the end of quadrant 2, that's where an angle will be 180 degrees. So angles between 90 and 180 will be in quadrant 2. Between 180 and 270 will be in quadrant 3. And then we go back to the beginning. Between 270 and 360 will be in quadrant 4. An angle that terminates on one of the axes is called a quadrantal angle. Naming of parts today. Quadrantal angles terminate on an axis. Angles in standard position with the same terminal side are called coterminal angles. So because we're going around in circles like this, we have this new idea of coterminal angles. These are places on that we can, the angles in standard position that will have different measures but be in the same location. This doesn't happen on the real number line. If you have two different locations on the real number line, they'll have two different values. But here, since we're going around from 0 to 360, we just get a copy of that from 360 up to 720. And it's all the same places. So what we mean is that this 270 degree angle, we can also label that as a negative 90 degree angle. So this 270 is also negative 90. Oops. I'm not writing anything secret. I just didn't scroll. So that 270 degree angle can also be negative 90. Those angles are coterminal. I can either get to this 270 degree angle going in the positive direction, 270 degrees, or in the negative direction, negative 90 degrees. So those are coterminal angles. Going around 270 to get to this terminal angle. Or negative 90. So what this means is that each angle between 0 and 360 has an infinite number of coterminal angles with different measure, but in the same place. So this is good. We only have to worry about what's going on between 0 and 360. This is bad because there are stuff before 0 and after 360. And so we have to know that this is possible. Any questions? Comments? Snide remarks? We're just naming parts. This is the part of the IKEA project where we pulled the instructions out of the box and we pulled all the bolts out. And we've just laid them all out to make sure we've got all our parts. We're just naming our parts. Now that we have angles in standard position, we have some more parts to name. We've got to name reference angles. Since all the angles going around, we'll have coterminal angles with lots of different names. One of the ways that we can organize things is through what we call reference angles. So if we have an angle theta, the reference angle will go from the terminal side of theta to the nearest part of the x-axis. So the reference angle goes from the terminal side to the nearest x-axis. The nearest part of the x-axis. So when we talk about reference angles will always be acute angles. They'll always be less than 90 degrees. So reference angles will always be acute angles, that is less than 90 degrees. So for example, let's look at a 120-degree angle. So a 120-degree angle will start with the initial side on the positive x-axis. We'll go counterclockwise 120 degrees. So that's going to go past 90 and then 30 more degrees to the terminal side. The reference angle will go from this terminal side to the nearest part of the x-axis. So the nearest part of the x-axis is going to be the negative x-axis. So the reference angle will fit in here. Here is our reference angle. And I'm going to denote the reference angle as theta sub r. So if we've got 120 degrees, how far is it to the negative x-axis, the negative part of the x-axis? How many more degrees do we have to go? 60 degrees. So our reference angle is 60 degrees. Any questions? Let's suppose that the angle gamma is 240 degrees. So if you think about a 240-degree angle, we'll start at the positive x-axis, start going around counterclockwise. 90 is at the positive y-axis. 180 is at the positive, or sorry, the negative x-axis. 270 is at the positive, or sorry, at the negative y-axis. So a 240-degree angle will be in quadrant 3. The reference angle will go from the terminal side of 240 degrees to the nearest part of the x-axis. So that will be the negative x-axis. And how many degrees do we have to go back to get back to the negative x-axis? So if this the negative x-axis is at 180, and we've gone 240, 240 minus 180 gives us a reference angle of 60 degrees. Our reference angles will always be positive acute angles. We just care about how far to the x-axis. Any questions? Yes. We go to the nearest one. It's kind of like when we were talking about rounding. So if we're here in the third quadrant, we're going to go back to the negative x-axis. If we're up here in the second quadrant, we keep on going to the negative x-axis. If we're in the fourth quadrant, if let's say I put angle beta in the fourth quadrant, so between 300 degrees will be between 270 and 360. So if this is where angle beta is 300 degrees, here we're going to go forward to the positive x-axis. We've got to get to the nearest part of the x-axis. So the reference angle for beta will be 60 degrees. Any questions? These are angles in standard position, and these are how you find the reference angle. We can write down formulas for how to find the reference angle based on the angle and quadrant. I guess in quadrant 2, we would take 180 minus the angle. In quadrant 3, we take the angle minus 180. In quadrant 4, we would take 360 minus the angle. But then we have to remember all these formulas, and formulas are terrible. We want to understand the concept of reference angle, not try to remember a bunch of formulas for reference angle. It's kind of like the slope formula. You don't want to have to remember the slope with the slope formula. Y2 minus y1 over x2 minus x1. That's not how you would say that anyway. If you understand what the slope means and what the slope is attempting to represent, you don't need the slope formula. The slope formula is just going to get in the way. If you need the slope formula, you don't understand slope. If you understand slope, you don't need the slope formula. Any questions? Then there are some formulas that are kind of like partially useful, like the quadratic formula. Quadratic formula is trash, the way we present it. It's got useful elements, but the way we say it and the way that we write it, and thus the way that we use it, is terrible. I can't believe we've gotten away with it so long. All right. So this is how we put angles in standard position. This is how we determine a reference angle for an angle in standard position. Let's combine this with some stuff from chapter 1 that we need to remember. I'm never satisfied with whatever word we want to use to describe these two particular right triangles. Iconic. I like that one. That's excellent. Because it combines all those things. Yes. Oh, I'm going to use that from now on. That's excellent. So the iconic right triangles are the isosceles right triangle, otherwise known as the 45-45 right triangle, and the 30-60-90 triangle. These are two triangles to know. So the 30-60-90 and the isosceles are the 45-45-90. I guess since they're right triangles, it's redundant to say the 90 part. So it'd be the 30-60 right triangle or the 45-45 right triangle. So let's start with the isosceles right triangle. Since these two angles, the two acute angles of the isosceles right triangle are equal, that means the sides opposite those angles are equal. So if I call one of them 1, then the other one is also 1. And the Pythagorean theorem tells us that the hypotenuse will be equal to the square root of 2. This means, because of the way similar triangles work, I can scale this up. So if the sides of the isosceles right triangle are increased to 10, I just multiply 10 times the square root of 2 to find the hypotenuse. The information that we get here is that the hypotenuse is square root of 2 times the legs in the isosceles right triangle. The other thing that we get out of this is the sine, cosine, and tangent of 45 degrees. So the sine of 45 degrees is opposite 1 over hypotenuse root 2. Because opposite and adjacent are the same, cosine of 45 degrees is equal to sine of 45 degrees. Cosine of 45 degrees is adjacent over hypotenuse. And tangent of 45 degrees is opposite over adjacent, or just 1. Now, you may or may not remember from your algebra class that we don't like having radicals in the denominator. And so we have to do what's called rationalize the denominator. We actually don't have to rationalize the denominator. The reason that you want to rationalize the denominator is that this number, the square root of 2, that goes on forever. It's a non-repeating, non-terminating decimal. So if you start off, take 1 divided by 1.41, and you want to improve the accuracy of your result, you have to do the division all over again, 1.414. The whole thing over again. But if we rationalize these expressions, multiply the top and bottom by root 2, I can rewrite 1 over root 2 as square root of 2 over 2. Now the denominator is just a 2. And if we want to get a more accurate result, we just tack on more digits from the square root of 2. Pick up where we left off. That's the rationale for rationalizing. Of course, it's not exactly something that's required anymore. If you want to know what the sine of 45 is, the decimal approximation, you just say, hey, calculator, what's the sine of 45? I had to clear it to make sure there were no embarrassing calculations for it. Say, hey, calculator, what is the sine of 45? Oops. And it will just tell you. But that's 1 divided by the square root of 2. So in an age of calculators, it's not really necessary to rationalize things. Rationalize denominators. Really quickly, on the other triangle, if we think of this as being half of equilateral triangle, if we imagine this is half of an equilateral triangle with a side where each side is 2, if I drop down the angle from the top, if I bisect the angle at the top, I'll get a 30-degree angle, and we'll cut the side opposite that in half and leave 1. Then the Pythagorean theorem will tell us that the vertical leg is going to be the square root of 3. So once again, start with an equilateral triangle with a side length of 2, and then bisect the top to get those each side as 1. Or bisect the base into 1 each. That's not how I wanted to say it. Picture. Now, we can use this triangle to learn the sine, cosine, and tangent of 30 and 60, because they're not the same anymore. So we can write the sine of 30 is opposite over hypotenuse. Cosine of 30 is adjacent over hypotenuse. I spelled 3 wrong. And tangent of 30 is opposite over adjacent. One over root 3 is not how we would usually list the tangent of 30, we would probably rationalize this if we want to fit in and be traditional, and write that as root 3 over 3. Checks out on the calculating machine. The tangent of 30 is root 3 over 3. Square root of 3 divided by 3. Or 1 divided by the square root of 3. But there's another angle. We have the sine of 60 is the square root of 3 opposite over hypotenuse, so square root of 3 over 2. Cosine of 60 is a half. Tangent of 60 is square root of 3 over 1. You don't have to memorize these 9 values, but you do have to know these 9 values. So if that means that you're going to have to sit down and memorize these 9 different things, then so be it. If you think that seems like a lot, that's only because it is a lot. And you have to remember all of it all the time in perfect detail. Don't worry, you know your times tables all the way out to 12, probably. And you remember that just fine. I don't know if you had to sit down and memorize those, or if you just remember them through repetition. You know what I mean? Back in the day, when we used to have to dial phone numbers, we couldn't just have our phone call people, personal assistant style. You would remember phone numbers. I remember my friend's phone number from when I was 12. Not because I sat down and memorized it. I just dialed it so much, I can't forget it anymore. It's like the words, the song that you know, you didn't actively memorize that. You didn't print them out and sit there and read them and try to remember, and read them and try to remember. You just sang the song so much that you just know them now. There's a difference between memorizing stuff and then just remembering. Like on the Animaniacs, there's that Yakko's World song. I actively memorized that because I was trying to win a bet. So I had a long commute at the time. I had a tape deck in my car, so I won that bet. I don't know if I can still do it. I can definitely do the first verse though. I can't not know that anymore. I can't just erase it. It's not like a computer where there's a file that you haven't used for a long time and you just delete it. Now, I still remember United States, Canada, Mexico, Panama, Haiti, Jamaica, Peru, Republic of Dominican, Greenland, El Salvador, and so on, if you're familiar with this. Incidentally, this is the only way I can remember what the capital of a state is. So if you ask me the capital of a state and it's not Louisiana, I'm not going to know right away. So I'm going to be like, oh, wait, hang on. Baton Rouge, Louisiana. Columbus is the capital of Ohio. There's Montgomery, Alabama, South of Hill, and then California didn't show up until way later. Fortunately, I live in California, and it'll be capital is over there somewhere. All right, let's take 5. Come back and combine this information with reference angles. So you got 5 minutes to memorize these 9 things. Is that? Yeah, I'm gonna not record the break. So video on pause.